Welcome to This Explainer. Today, we're jumping straight into the harsh, terrifying, but honestly, absolutely fascinating physiological realities of the human body in the extreme environment of space. And to help us wrap our heads around these deadly physics without getting, too unbelievably gruesome, we're gonna imagine a brave little astronaut cat and its animal friends guiding us through the cosmos. Let's get into it.
So let's tackle the ultimate pop culture question right off the bat. If you were out there floating in the void and you just took off your helmet, what exactly happens? Would you instantly freeze solid like a popsicle? Or would you just explode into a million pieces? I mean, we've all seen those crazy scenes in sci-fi movies, but what does actual biology say?
Section 1. Hollywood myths versus space reality. To get to the truth, we really have to separate cinematic drama from verified astrophysics.
Okay, so the crucial point here, you wouldn't actually explode. Human skin, or even the skin of our hypothetical feline astronaut, is incredibly tough and elastic. It's wrapped in strong connective tissue, acting like a surprisingly good pressure vessel. It's totally capable of keeping your organs inside. But you would experience something called abulism, which honestly is way more gruesome than just popping like a balloon.
So, what is ebulism? Well, it's the formation of gas bubbles in your bodily fluids caused by a massive sudden drop in atmospheric pressure. You see, without Earth's heavy atmosphere pressing down on us, the boiling point of liquids drops dramatically. This means the water inside your blood and your tissues rapidly expands, turning directly into gas. Deep inside you. You'd rapidly swell up to about twice your normal size, puffing out as trapped gases expand under the skin. Yeah, definitely not a great feeling for our astronaut cat.
Section 2. Crossing the Armstrong Limit. Now, to understand exactly when this horrific process kicks in, we don't even need to look that far away. Because you actually don't have to leave Earth's orbit to be in mortal danger. Right at the Armstrong Limit, which is an altitude of about 19 kilometers or roughly 12 miles up, the atmospheric pressure is just so incredibly low that water boils at exactly 37 degrees Celsius. And guess what? That happens to be normal human core body temperature. So, past this exact threshold, your own body heat literally boils your internal fluids. You absolutely need a full pressure suit to survive, even just in the upper atmosphere. And tragically, we know the deadly reality of this limit from history. Back in 1971, a pressure equalization valve unexpectedly opened on the Russian Soyuz 11 spacecraft while it was 168 kilometers up. The crew was fully exposed to the vacuum high above the Earth. They remain the only 3 humans known to have died directly from exposure to the vacuum of space, proving that pressure equalization is literally our most critical lifeline. Section 3. The vacuum death timeline. Let's break down exactly what happens to an unprotected body in a total vacuum, second by terrifying second. This timeline is pretty grim, but it highlights something surprising. It's actually the lack of oxygen reaching your brain that knocks you out first. Within just 10 to 15 seconds, freshly deoxygenated blood reaches your brain, and boom, you lose consciousness. By 90 seconds, you're dealing with massive embolism. Your blood is actively boiling, and your rapidly swelling muscles cause something called vapor lock in your heart. Basically, a gas bubble enters the heart chambers, totally preventing the muscle from pumping any liquid blood at all. By the 2-minute mark, with circulation completely stopped, you're facing likely death from asphyxiation. And it's super counterintuitive, but you absolutely cannot hold your breath. The vacuum actively rips the air right out of your lungs with extreme force. After that initial rush, it fiercely pulls water vapor from your airways. And because evaporation actively absorbs heat energy, it rapidly plunges local temperatures. So picture our little astronaut cat. While its body is uncomfortably swelling up from all that internal pressure, its nose, tongue, and throat would simultaneously feel a searing flash freeze, instantly getting frostbitten from the rapid moisture loss. It's a bizarre mix of boiling inside and freezing outside. Now, this isn't just some grim theory. We actually have an incredibly visceral quote from a NASA test subject who survived a near-fatal 14-second vacuum exposure back in 1965. His spacesuit leaked in a vacuum testing chamber, and his account perfectly anchors the surreal, terrifying reality of what ebulism physically feels like right before everything goes black. He remembered the saliva on his tongue actually beginning to boil.
Section 4. The space temperature paradox. Once we've grasped the immediate pressure problem, we really have to tackle a massive conceptual misunderstanding about the thermodynamics of space.
You see, temperature is essentially a measure of how much energy atoms and molecules have to vibrate and move around. But space is a vacuum. It's mostly empty, so it doesn't really have a temperature in the traditional sense.
It completely lacks the atoms needed to transfer heat via conduction or convection. Think about it. If you touch a hot stove, that's conduction. If you feel a warm breeze, that's convection. Neither of those can happen out there. This means heat can only be lost through a very, very slow radiation process, where your body just emits electromagnetic waves into the void.
And this brings us to the great paradox of space thermodynamics. Imagine our cat floating in direct, unfiltered sunlight. Without an atmosphere to scatter that solar energy, it would feel an overwhelming, scorching heat, literally baking at temperatures up to 120 degrees Celsius, all while getting an extreme, blistering UV sunburn. But imagine its friend, the dog, floating just a few feet away in deep shade. The dog wouldn't instantly turn into a rigid ice cube like in the movies. Because a vacuum is actually a near-perfect insulator, the dog would just feel a slow, creeping chill. It would slowly radiate its 900 watts of body heat away, taking several hours to completely freeze in the dark.
Section 5. The invisible radiation threat. So let's say you somehow manage to survive the lack of pressure and those wild temperature swings. Well, there's a third, invisible, and far more long-term killer waiting for you.
NASA actually summarizes the holistic physiological threats of human spaceflight using a really handy acronym, RIDGE. That stands for radiation, isolation and confinement, distance from Earth, gravity fields, and hostile closed environments. Now, altering gravity and psychological isolation are massive hurdles, for sure. But radiation is the most persistent and unavoidable danger of the entire bunch.
Here on Earth, our powerful magnetosphere and thick atmosphere provide this incredible protective cocoon for all life. But the second you venture beyond that invisible shield, human DNA is exposed directly to high-energy galactic cosmic rays and sudden solar particle events. And we're not just talking about invisible rays here. These are actual atomic fragments, stripped of their electrons, traveling at nearly the speed of light. They will literally tear right through human tissue and microscopic cellular structures. Without heavy, dense spacecraft shielding, this radiation just wreaks absolute havoc on our biology. In the short term, it damages lymphocytes, which severely lowers your immune system. Looking long term, it significantly increases the risk of various cancers, causes severe cataracts in the eyes, and recent NASA-supported studies show it can even accelerate the onset of Alzheimer's disease. Oh, and if a rare, massive solar flare hits without warning, that can deliver an acute, fatal dose of radiation in just a matter of minutes. We have extensive modeling of deep space transits and the Martian surface that shows just how drastically these radiation doses fluctuate based on active solar cycles. Take the human brain, for instance. During a solar minimum, when the sun's magnetic field is relatively weak and lets way more cosmic rays into the solar system, the equivalent dose rate hits 1.74 times 10 to the third millisieverts. That's a massive jump compared to the 1.27 times 10 to the third during a solar maximum. This data proves, beyond a shadow of a doubt, that perfectly predicting solar cycles and engineering massive physical shielding are really our only defenses out there. Which brings us to a final thought for today's explainer. We've imagined our brave little cat enduring boiling internal fluids, a flash-frozen nose, scorching heat, creeping cold, and invisible cosmic radiation. It's a totally sobering reality check. It really leaves us wondering, is human biology simply too fragile for the extreme, unforgiving physics of the cosmos? Or will our incredible engineering continue to overcome our natural limits so we can one day safely explore the stars? Think about that the next time you look up at the night sky. Thanks for hanging out with us today.
Knowledge grows through sharing. What are your thoughts on today's topic? Let me know in the comments below. Don't forget to subscribe as we continue to grow together.